Good morning. Today we shall see about the spectrum analyzer. So spectrum analyzer is a measuring instrument that is used for microwave operations. So the spectrum analyzer measures the amplitude of an input signal versus frequency within the full frequency range of measurement. The oscilloscope that we are using in the lab experiments measures the time domain. So the spectrum analyzer measures the frequency domain. That's the difference between the spectrum analyzer and the oscilloscope. In frequency domain, the complex signals are separated into their frequency components, and the level at each frequency is displayed. So using the spectrum analyzer, the amount of noise present in the spectrum, that is frequency domain, can be reduced. Their impact in the measurement can be reduced, and also the spectrum analyzer will ensure that there is no interference from the neighboring frequencies. So we can measure the microwave frequencies using spectrum analyzer with less amount of noise. Then we shall see about the block diagram of our analyzer. So there are two types of spectrum analyzer. The first one is swept type of spectrum analyzer, and the second one is Fourier spectrum analyzer. So this block diagram is for swept type of spectrum analyzer. So the principle of operation of this swept type analyzer is, first the signal is the signal to be displayed using this spectrum analyzer is connected to the input of the analyzer. That is, the input part has an RF input and attenuator. So in this input part, we will apply the input signal, and then the signal is combined with the local oscillator through a mixer to convert it into an intermediate frequency. So the second part is converting the input signal into an intermediate frequency signal. Then these signals are sent to the intermediate frequency filter, where the output is detected and the presence of the signal at the analyzer's tuned frequency. So if the input signal exceeds the operating frequency of the analyzer, it won't be displayed. This is how this analyzer is working. So we shall see the characteristics of this analyzer. So there are 9 characteristics: suitable input level, maximum input level, measurement frequency range, sideband noise, resolution bandwidth for frequency, RBW and Sweep Time, detection method, video filter, then dynamic range. So the first one is suitable input level. So in the block diagram, I have shown that we are using the local oscillator and mixer. So the local oscillator and mixer has some higher operating frequency. Beyond that, it can't operate without creating noise. That is more number of noise. So since we are using the local oscillator and the mixer in our spectrum analyzer, based on the operation of frequency of operation of these two things, that is local oscillator and mixer, the distortion level specification is made using this local oscillator and mixer. So the level of relationship between the input signal and the distortion is specified at the mixer input level and not at the input connector. So that is the purpose where we are using an attenuator at the input side. So this RF attenuator attenuates the input signal to a suitable mixer input level, and then the suitable input is mixed in the mixer. The second characteristic is maximum input level. So the maximum input level, in the sense, the maximum input that can be given as an input inside the spectrum analyzer. So the maximum input level is based on the attenuator and mixer characteristics. If we give any signal beyond the maximum input signal, it will damage the entire circuit. So for that purpose, we are using an attenuator in the input side. The third characteristic is measurement frequency range. The measurement frequency range is determined by the sender frequency of the intermediate frequency filter, that is IF filter, and the local oscillator frequency range. So it is given by input signal frequency is equal to local signal frequency minus IF filter frequency. So the input signal and the local signal are mixed by the mixer, and the mixer output is filtered by the IF filter with sender frequency FC and displayed on the screen. So based on this input signal frequency, the measurement frequency range will be applied to the spectrum analyzer. Then sideband noise. So limiting the sideband noise is very much needed, as if sideband noise is very high, the spectrum analyzer can't make uh, measurements in its output. So limiting the sideband noise is very much needed. The sideband appears in the base of the spectrum. Since we are using a lot of oscillators, filters, and all, it may produces some small amount of noise. So this noise can't be eliminated completely, so that there will be a small amount of sideband noise. But the sideband noise below the threshold level is very good. If it exceeds the threshold level of operation, it's very difficult to measure the spectrum. Then the sideband noise shows the signal purity, and the performance of the nearby signal analysis is determined by this characteristic. So the sideband is specified by how many dB that is down the center of frequency at an offset of 10 kilohertz or 100 kilohertz, while the resolution bandwidth is narrow and a high purity signal is input. So this is what I said as the threshold. So generally this sideband noise must be below an offset for good measurements. And the next characteristic is resolution bandwidth for frequency. So resolution in the sense, sometimes there may be we need to measure two input signals as in the spectrum analyzer. Instead of giving one input signal, there may be scenarios we need to give two input signals. So the capability of the spectrum analyzer to show or measure the two input signals is known as resolution bandwidth for frequency. It is termed as RBW. The two input signals can be seen as two spectrum waveforms, and it must exceed the 3 dB bandwidth of the IF filter. This 3 dB bandwidth of this IF filter is called as resolution bandwidth. So using this 3 dB bandwidth only, we can measure the two input signals simultaneously. When a narrow RBW is selected, the 3 dB bandwidth and 60 dB bandwidth becomes very small, since we are choosing a very narrow bandwidth. The frequency resolution will be very higher, and the average noise signal will fall, and we can see the very low frequency signals also. And the next characteristic is RBW and sweep time. So based on this sweep time, the wave will either appears or disappears. If the sweep speed is not proper, the wave may skip the output screen. So an optimized value of sweep time needs to be adjusted using the knob. So you consider the wave that is displayed in the screen. A signal displayed with proper sweep time is shown in the wave as numbered as 1. In second and third wave, the amplitude of the display decreases. The reason is the sweep is made too early and the frequency shift. So having a proper sweep time is an important characteristic of spectrum analyzer. So sweep speed will determine the quality of the output signal. And the next characteristic is detection method. So as shown in the block diagram, the final block is detection. Detection in the sense the baseband signal that is allowed as input into the spectrum analyzer. So these are 5 types of detection methods. The first one is normal. In normal detection method, it displays both the maximum level and minimum level present between the current sample point and the next sample point. In POS peak type of detection method, it displays the maximum level present between the current sample point and the next sample point. So generally, we will use this POS peak type of detection methods to measure the peak value of signals near the noise level. So mostly it will be used for peak measurements. The third type is sample detection method. It displays the instantaneous signal level at each sample point. This sample is used for noise level measurement and time domain measurement. And the fourth one is negative peak. This negative peak type of detection method is used for detecting the minimum level of signal present between the current sample point and the next sample point. And the final RMS detection method is used to display the root mean square value of the signal input between the current sample point and the next sample point. So all these detection methods will work based on our requirement. So if you need to measure the positive peak, we will use POS peak. If you need to measure the negative peak, we will use negative peak detection method. Similarly, the normal will measure both the maximum level and minimum level. So based on our requirement, these detection methods will change. And the next characteristic is video filter. So when a small signal is included in noise is measured, this effect is used. Basically, it's a low-pass filter. It is used to extract the signal from a noisy environment. So it is used to remove the noisy signal by lowering the VBW. So if by lowering the VBW, we can measure the signal that is present in the noise. But if we are decreasing the value of VBW very high, the signal will disappear. So that an optimum value of VBW needs to be maintained. And the final characteristic is dynamic range. So dynamic range is the range that can be measured without making any noise. That is the amount of signal that is measured from a noisy environment. So the noisy environment is that characterized by 3 things. The first one is noise level, and the next one is residual responses, and the final one is distortion. So first we shall see the average noise level. This average noise level is the internally generated noise level, that is from a local oscillator or some filter. It may generate some amount of noise during its operation or harmonics. So average noise level is the thermal noise and the other noise generated from the active elements like transistors and ICs. So this average noise level must be below the lower limit of the input signal level. Otherwise, if this average noise exceeds the input signal level, the signal can't be measured. The next characteristics of noise is residual response. So it is the phenomenon that it appears as an input signal on the screen even though there is no real input signal. So since we are using the local oscillators in our circuit, these local oscillators will generate some frequencies. That's the operation of oscillator. So even though we are not giving any input signal to the analyzer, this local oscillator will tend to generate some signals internally. So this may appear in the screen. So this is known as residual response. So this residual response will appear when the basic waveform and the harmonic components are mixed, producing the IF frequency. So these residual responses will appear in all frequency bands and in the average noise level. So this residual response can't be completely eliminated since we are using the oscillators. And the third characteristics of noise is harmonic distortion. So since due to the usage of mixer and local oscillator as well as IF filter, the harmonic distortion can be prevented, but it can be minimized. The second harmonic and third harmonic of the input signal that is occur in the mixer generating the distortion when a high level in signal is input to the mixer. So when a high level signal is given as input, this harmonic distortion will take place. And the first type is swept-tuned spectrum analyzer. As I said earlier, it reads the frequency range, displaying all the frequency components present. That is measuring in frequency domain. It enables the measurements to be made over a large dynamic range and wide frequency range. That is an advantage of this. We shall see the components of the block diagram one by one. The first component is input attenuator and mixer. So the purpose of input attenuator is to adjust the level of signal that is entering into the mixer. So the mixer has an upper limit of accepting the input signal. So the basic characteristic of attenuator is to attenuate the input signal to the optimum level that is acceptable by the mixer. If the signal is too high, the readings will fall outside the display, but also the mixer performance may not be optimum. So as we know that a mixer is a 3-port device that converts a signal from one frequency to another. So this input attenuator and mixer setup is very much needed as we are using the mixer component here. And the second part is gain, filter, and detector. As we have seen in the block diagram, there are a large number of IF stages available in the spectrum analyzer. These IF stages are used to provide the gain of the signal. Without gain, it's very difficult to display the low frequency signal using spectrum analyzer. So to boost up or improve the input signal, we are using these IF stages. So based on the gain of the IF stages, the signal clarity will be more. So it is used along with the RF gain control. Too much of IF gain will increase the front-end noise level, which may result in low-level signals. The IF filter is a band-pass filter that is used as a window for detecting signals. That is the low frequency baseband signal. Its bandwidth is also called as resolution bandwidth. The analyzer will convert the IF signal to a baseband or video signal so that it can be digitized and viewed on the analyzer display. So this is accomplished by using an envelope detector whose video output is then digitized and converted into digital using an analog and digital converter. The next component is video filter, local oscillator, SG and ADC. So the video filter is a low pass filter that is located after the envelope detector and before the analog to digital converter. So since we know that the baseband signals are of very low frequency, the video filter will extract those low frequency signals, and then the frequency components will be detected using the envelope detector, and then it is converted into digital by using analog to digital converter. So this filter determines the bandwidth of the video amplifier and is used to average or smooth the signal that is displayed on the screen. So the local oscillator must be capable of being tuned over a very wide range of frequencies to enable the analyzer to scan over the required range. Generally, we are using this spectrum analyzer for a wide range. That's why the local oscillator needs to be capable to measure all this wide range. The sweep generator tunes the local oscillator so that its frequency changes in proportion to the ramp voltage. So this ramp voltage is to measure the signal in frequency domain on the x-axis. So then we shall see the advantages and disadvantages. The advantages is it can operate over a wide frequency range and it has a wide bandwidth. It is not as expensive. This spectrum analyzer is somewhat cost effective than other type of spectrum analyzer. And the disadvantage is it cannot measure the phase and it cannot measure the transient events. The next type of spectrum analyzer is Fourier transform spectrum analyzer. So it works based on the FFT. So this analyzer takes a time domain signal, then it digitizes the time domain signal using the digital sampling based on the sampling theorem, and then use the basic computations to convert it into the frequency domain. So it's performing or processing the signal in time domain, and in the final stage it is converting it into the frequency domain, and the result is displayed as a spectrum. So here we are using a variable gain or attenuator to attenuate the signal. That is the input signal is attenuated to the signal that is given as that is the signal that is required by the low pass filter, that is acceptable by the low pass filter, and then the low pass filter will remove the noise components in the signal, and then the signal is sampled or digitized, and then sampled and then digitized in ADC, and then FFT analysis is done, and then the spectrum is displayed using Fourier transform spectrum analyzer or FFT spectrum analyzer. So the operation is given as it takes the entire frequency range at the same time and using parallel filters for measuring simultaneously. Since we know that in FFT the parallel operations are going on, we need parallel filters to measure the things. It is actually capturing the time domain information, and from the time domain information the frequency information is extracted so that it can measure both the phase as well as magnitude. So the applications of spectrum analyzer is, this spectrum analyzer is used in very low frequencies measurements like biomedical electronics, geological surveying, and oceanography. It can be used in analyzing the performance of AM and FM transmitters. So thank you for watching.
Yeah.